All right, so we were just finishing up this proof. So we want to prove that B prime is contained in B, and so we talked about, so let's suppose we have an element in B whose degree is greater than or equal to D. Then what we can do is we can basically, what we're going to do is for every single coefficient, which is associated with a power of x which is greater than or equal to D, we're going to get rid of it by taking combinations of these things. And the thing about these things is these things could have different degrees which are sort of all over the place, and we got to get them all on the same level. And in order to do that, we need to have enough room to bring them up to the same level. And in order to do that, we need to multiply these things by powers of x. And in order for this to work, like this only works when the degree is beyond D, because otherwise these things, like, you can't get them to line up at all. So anyways, so take this polynomial whose degree is greater than or equal to D, and let A be its leading coefficient. Then we can write it as a linear combination of the pi's. And then what we do is each pi is the leading term of fi. And we want this fi to have degree precisely equal to df here. And in order to do that, what you do is you take the polynomial fi and you multiply by x to the power of df minus the degree of fi, because then you just add the degrees up and you get the degree of this thing to be df. And so if you look at the leading term, the highest power of this sum here, the coefficient is going to be precisely the sum from 1 to n of the a1, I pi's. But that's just a. And so the leading coefficient of this entire thing is going to be, well, the leading coefficient, or the leading term of this is a, the leading term of this thing is minus a when you have the minus in there. So that's going to cancel out the coefficient associated with the highest degree. And so therefore this thing will have degree which is strictly less than the degree of the function we started with, df. Also note that f is in B and each of the fi's is in B, and B is an ideal, so multiplying it by this thing and taking the finite sums keeps you in B. So therefore this entire thing is in B. Okay, so now we've taken some sort of strange looking we've done some sort of strange looking manipulation to our polynomial f so that we stay in B but manage to lower the degree. And so this polynomial here, this difference, will have a new degree. You could call it like D2 or something. And maybe D2 will, suppose that D2 is also greater than or equal to D. So we've brought the degree down a little bit, but not low enough. Then you could sort of do the same thing, but instead of it, but this time we do it to the power D2. And so we use that to get rid of that thing. And so you continue this process over and over, and what happens is you'll end up with f, and then you'll subtract, well, we first subtract this, this is fi x to the whatever, it's just the d, this thingy, and then you just keep doing it. Here, we'll call it di. We'll define this to be di. So this is a1, I fi x to the di minus blah blah blah, and this will be a sub ki. Oh wait, no, this is, we'll call this dk, not for Donkey Kong, but for, this is the, no, this will be d1 because this is like the first iteration of the process. And now since this is the kth iteration, this will be fi x to the dk. So Donkey Kong is here and not here. So anyways, because every single time we do this, we decrease the degree strictly, and because this is a polynomial, which means that it has finite degree, this will eventually, after say k iterations, get us to the point where we have something of degree which is strictly less than d. So suppose that these things are all chosen correctly, and suppose that k is large enough. We've done this process so many times that this thing here, this sum or difference, whatever you want to call it, is finally of degree strictly less than d. Recall at every step, this is in B, so this is an element of B. And as we've proven before, okay, so now take this thing and we'll call it G. So G has degree strictly less than D, and it's an element of the ideal B. So therefore, by the first part of our argument, we know that it's contained in B prime. So this whole thing here is contained in B prime. So now, so f minus these things is equal to g. Now you take all of these sums here and just move them over to the other side, and what do you get? You get f equals g plus this sum, again, this should be a1i fi x to the d1, and this should be a ki fi x to the dk. And so G we know is in B prime, and each of these sums here, like, oh, okay, so of course here, obviously these are in B because each of the FIs is in B, but because the FIs are generators for B prime, each of these sums is also in B prime. And that's because, like, what we're multiplying is by elements of the polynomial ring, and of course this is an ideal in the polynomial ring. So that's another thing. When we say an ideal generated by things, you need to be careful, like, where they are, because here this is the ideal generated by these things in AX, so you can take elements in here and multiply them by polynomials. Whereas here, this was this module was generated in as an A module, so you can only, so things in here you can only multiply them by things in A, not by polynomials. Anyways, okay, so we have this f is equal to this whole thing, and all of these things are things in B prime, and so their sum is in B prime. So in this case as well, we can prove that f is contained in B prime, and this holds for every single f in B because it holds regardless of the degree. Because it holds regardless of the degree of f. So therefore B is contained in B prime, and since we proved already that B prime is contained in B, we have that B is equal to B prime. And in particular, since B prime is finitely generated, B is finitely generated. And since this holds for every single ideal B, we know that every ideal in A adjoint X is finitely generated, which means that it is Noetherian. And therefore, if A is Noetherian, then so is the polynomial ring, and this concludes the Hilbert basis theorem. And yeah, I think this is pretty much all we have to say about ring theory. There's some other stuff I've learned about, like Artinian rings, but I think this is the stuff that I'm mainly concerned about, because part of why I do this is because it helps me study so that I hopefully do well in the class and can continue the program that I'm in. So yeah, I might do some more videos doing exercises and stuff, but this should be the last video that I have on ring theory. Alright, well, that wraps up our section on rings. Hope you learned something. If you didn't, not my fault. We forgot to do radicals.